Hamiltonian and Lagrangian where we demanded that the potential not be a function of velocity, so that you could build the equations, otherwise you didn't have it. Well, today, with our introduction to the electromagnetic Lagrangian, that is, a charge in the electromagnetic field mechanics, we're going to have potentials that are functions of velocity. So I want to go through the vector analysis and the Lagrangian Hamiltonian analysis for that case. And then we'll go look at the mechanics that comes inside a cyclotron or Hall effect, a very simple model of the Hall effect, and show some simulations of that, plus a mechanical analog for the cyclotron. And I'll introduce you to the FBI rule, which you should know if you're going to live in this country for very long, and also cycloid geometry if we have some time. We're going to look at that because that's what we get against cycloids and trajectories when you put it in a field that's constant. So let's take a look first at the vector analysis and the FBI rule. This is the so-called ponder-motive form of Newton's F equal ma equation for a mass charge E, say an electron, which is 10 to the minus 19 times 1.6 roughly. And the scalar field would be designated by a uppercase V, vector potential by a vector A, and both of these are functions of position in general. The electromagnetic equations, that is Maxwell's equations for potential, is a definition that you've seen, I hope, in your electromagnetic class. But we're adding this extra thing here in order to have Hamiltonian that's a function of velocity. So the partial derivative of a thing called the vector potential, whose curl is the magnetic field, is part of this ponder-motive equation here, the being curl of A. So we have to work out the vector algebra of putting that inside this and then get it into a Lagrangian form. This is called the minimal coupling Hamiltonian or minimal coupling Lagrangian for reasons that I'll try to explain later a little bit. In any case, right now we're just dealing with what I call the FBI rule, and that will be the hand-waving, literally hand-waving thing for, if you're going to teach any students about electromagnetism, probably a good idea to do this. Everybody's heard of the FBI, and what we're talking about is force, magnetic field, and then I for current. That means some charge going at some velocity. And the velocity here, V cross B, this is basically the ponder-motive law that we're talking about, a second term in that F equal ma equation. Now the idea is that you're looking at your right hand. You have to use a right hand because this is the FBI. The FBI agents carry guns, so make your hand into a gun, but sort of have a trigger finger perpendicular to the main index finger, and then your thumb, if you can make it straight and perpendicular, you would have a coordinate system, a three-dimensional coordinate system. So the first thing you have to do is, starting with this finger here, put F, B, and I, and then that is the right orientation of the current, which is the electric charge times the velocity. B, the magnetic field, and then F, the force that's driving this ponder-motive system. So this is what we'll use to test the various things that we get for their the correct sign, and the subsequent dynamics will then make some sense. Now, what we have to do is take this apart in order to get the form of the equations that would make up a Lagrangian set. And we have a couple of things here. Some bookkeeping that I want to make sure you're familiar with. And this involves the second tensor that's just ones and zeros and minus ones. In this case, there's a delta function. The delta ij is a second-rank tensor that is symmetric, and ones and zeros depending on whether the I and j are equal. This is kind of the opposite. This thing is only non-zero when all of the indices are different. And it is anti-symmetric to their permutation. So this is a definition of the epsilon Levi-Civita. I'm probably not pronouncing it terribly well. But the idea is fairly simple, that this thing will be plus 1 for any even permutation of, say, 1, 2, and 3. But let's just say I, j, and k here in general. It will be 0 if any of these are equal, and it will be minus 1 if it's an odd permutation of 1, 2, and 3. So we could write all of these things here equal to 1 if we picked an I, j, and k. And then we could write them as minus that if I do a permutation of just a pair here, like I turn the I and the j around. Well, that's going to make a minus sign. I turn the j and the I around on the outside, and then here I turn these I and j's around. I get a minus sign. But any permutation that's odd gives you a minus sign, assuming that you had the value that would have given you something that's not 0 to begin with. Okay, now that's the tensor that's used to define a cross product. And so if I do a cross product of the ith component of the velocity and then the jth component of whatever this thing is, single vector, I would say that I would be looking for the kth component of this combination here. I would say, okay, I'm going to sum over I and j, and here ordering matters because if I flip these around, I may get a different sign. So I will have the convention that I just pick the component here be the first one, and then the other two would be the second and third in the index there. And then inside this collection here, I have a partial derivative with respect to coordinate A, and then coordinate B, okay, of A, and then that's the jth component of this thing, which is being summed over this thing. So it's the usual dummy index rule. Repeated indices are being summed over 3 in this case, all 3 components of space. So we need here an identity, which is sort of easy to prove just by trying a few of the cases, and that is that when I have a situation here where I'm summing over, say, k, I, j, a, b, j. I'm summing over the last index here. This works. Of course, I can cycle the j through to any of the positions, provided I do it in a way that leaves an even permutation. Then it's going to be equal to a plus sign in front of the case where k and a are equal, while I and b are equal. And obviously they'll have to be equal to different numbers in order for these things to not be 0. And then the permuted version of this thing with a minus sign is when the k doesn't equal A but equals B, and the I equals A. So it's just a switch here, KA and KB being the switch, and I'm leaving the form of this thing in the same, well, the same order that it comes in this sum right here. So I'm taking the case here where I'm summing over J, and these are 4 indices that I can play with. These are the 4 indices showing right here. So once you've done that, once you've broken this thing down, and then it's very easy to take that cross product, V cross the gradient cross, the curl, apart. So I have here this delta function hitting this thing, and then I have this delta function multiplying the same thing. So now I'm basically saying, I look here and I say, okay, I've got to set this A equal to K, and I've colored that to indicate that that K is not part of a sum. So I will be making those equal, and then doing the same thing down here with B, okay, B being equal to K and A equal to I. Here B is equal to I and A is equal to K in this monomial that involves the derivative and the vector potential. So I'll end up here then with I equal to B and A equal to K, and that's a sum over B. It's repeated. So I bring that out, separating those two. They're just numbers now, so I can permute this thing. I can't be doing is permuting those guys, so I have to leave them in whatever order they came. Same thing for this. So you take that thing and put it all together in a combination here. I'm seeing a partial with respect to K of VA minus partial K with respect to B, partial K of the velocity of the B component here is being subtracted. This is just a differential relationship for getting this product expressed in terms of a partial K of the product of A and V. So I'm just taking out the other combination there. And we turn this then back into the notation we're more familiar with. This is the gradient dot V right there. This is a V dot, a gradient of A. That's what this is. Right here's the vector made out of the derivatives. And then we're seeing that equal to these two terms right here. So actually two identities are being developed at this point just by using this epsilon tensor. So I recommend this highly in the sense of otherwise you have to remember identities. It's difficult to do Gibbs notation because its calculus is sort of ambiguous. This is much less ambiguous. So you're converting this thing back to this Gibbs bold notation using those. And there's one more thing that's involved here. Normally, all three of these terms would be non-zero, but in the Newtonian or Lagrangian mechanics, there's no explicit dependence of the position on the velocity or vice versa. So that quantity, that's this guy right there, gradient of the velocity, is identically zero. So we get to lose that, and that's a big plus. That's what makes all this work right there for getting the mechanics. So this thing here breaks up for this particular thing. Now this is for particle mechanics, where the velocity and position are independent variables. So a real take-home message here is that tensor index notation helps to distinguish things like this and this and this very nicely. Okay, now let's build a Lagrangian. Once we've got this thing opened up to that, we can do it fairly easy. This is Lagrange trickery again, the same type of trickery we did when we first derived these equations. The chain rule expansion is at work here, or will be used here. The idea that a total derivative of the a with respect to time, which includes it being a function, start with the differential dA, is equal to partial a with respect to x dx, and partial y dy, partial z dz, plus the partial, well, just the extra term that you need here would be partial a with respect to time. Explicit time dependence is being considered here. Partial t dt here, so we'd have dx, dy, dz, dt. That's one side of lemma 1, and now here are the derivatives. So we're going to have a partial derivative of a with respect to time plus these components of velocity dotted with the differential operator with respect to x, y, and z. So you can argue that if it didn't have this term right here, this is just a streaming derivative. It's just taking a gradient of a and multiplying it by the velocity to check for each component. All right. This guy right here, just change the position of it. Gradient of phi is going to want to have that combination as it turns out. And so we're going to be able to, if things go right, we would be able to get the gradient of the potential, which is only a function of r, and possibly time, and v dot a. Okay? That's this much of this thing. And then we have right here the total derivative of a, the time derivative of the vector potential. Okay? And that lets us rewrite a couple of things here. This is some of the trickery is I can insert a phi term like this into this expression right here. This is the derivative with respect to v, because this step requires it to scalar potential not have any v dependence. So we're still going to demand that of the scalar potential, but the a terms are going to have v's in them. And finally, this part right here that comes with this, I can put a partial derivative here. That's the gradient. This gradient right here is just being expanded. Again, inserting a v dot v term
so, Dr. Harter,
that has zeros for the gradient.
So, Dr. Harter, the one term is in the parenthesis, like d by dt of partial d by partial v, that one becomes the kinetic energy of the electromagnetic field. Is it like that one? Is that analogous?
Well, that remains to be seen. We're going to argue about that. But what we're getting here is a Lagrangian. You see, I have here d dt partial respect to velocity, okay, equals partial derivative with respect to r of just the kinetic, right? So basically it comes down to, momentum, it looks like, that with the right derivative. So this is what we're after, okay, once we've got both of those things set, okay? So Lagrangian has a linear velocity term, v dot a, in addition to the usual quadratic part, mv squared over 2, and then subtract the scalar potential. Okay, there it is. But add a V dot A. Okay. And that's called minimal coupling. This is the simplest expression I could make out of a velocity and a vector potential, scalar property. So that's, I think, the reason for that name. It's a high energy physics name. Okay. Now, let's look at what it does. Now, all of our stuff, if this is a Lagrangian, then the momentum should be the velocity gradient of this Lagrangian. It's now a function of velocity, so let's go for it. It's a very hairy function of velocity with this extra stuff right here. Okay. And you can see, not getting anything from that, but I am getting this and that. There's usual MV, and here's this. It's really remarkable. I mean, this is telling you all sorts of things. It's telling you that this vector potential is going to go in there and it just simply add to your ordinary momentum, to give you a momentum that you should be paying attention to. The one that's going to determine the quantum mechanical properties is this one. So this is putting extra kinks in your K vector and making your momentum either larger or smaller. It's taking kinks away. So that is what we have. And what you notice is that we have 1/2 mv squared here, and just when you take this apart here and take the partial derivative of v with respect to that, you get v dot v minus phi right here, okay? And this would be the case for the vector potential equal to 0. So we come back to the ordinary momentum in that situation. Now, the usual form of the Lagrangian with a scalar is there if this magnetic potential isn't there. Okay, now, the canonical momentum is the usual form for this, but it's this bizarre form for this. So this is the new thing here. Now, with the A, it leads to an extraordinary canonical momentum, namely this, and the particle momentum, this thing that we are used to at least calling that, is related to this canonical momentum by subtracting the particle momentum. mv is p minus that. In other words, this one right here is a boost of a velocity positively. This is a boost of a momentum negatively. Okay, now let's look at the Hamiltonian formulation, the one that tells us about energy, not phase.
Dr. Harter, can you go to the previous slide, please? Just have a question.
Yeah.
Yeah. So in an electromagnetic field, we know that the total momentum of the field is the mechanical momentum plus the momentum due to the electromagnetic field.
By the vector potential.
Characterized by the vector potential.
Right.
Now, we know how to measure the mechanical momentum because we know what the mass of the charge is, we know its velocity. And once we know what the field is, in this case, once we know the vector potential, we also know what the momentum, what part of momentum is contributed by the electromagnetic field.
That's right.
But when we write
two parts right here, this is what I want to look at.
So when we write mv as p minus e times a, how do we independently measure p? Is there a way to measure the total momentum of a field? Or is it just a mathematical construct that...
Depends on the gauge. Yeah. No, let's go look and see what happens when I substitute this back into the way I would want to do if I'm going to make a Hamiltonian, because I've got the Hamiltonian has to be a function of this thing explicitly. That's what's allowed, right? So let's look and see what that comes out to be numerically first. Okay. We've played this game sort of when it didn't really matter. This time it really matters. So I'm going to use the Poincare-Legendre identity for the Hamiltonian. That's velocity times momentum, the action, reduced action, minus the derivative of the action, Lagrangian itself, v dot p minus L. Okay, v dot this p, the p that's got the vector potential with the plus sign, okay, minus L. Okay, and here's the L in the form that we just worked out, with a minus of that, all of that stuff. Okay, well, look what happens. Vector potential disappears. So here's the answer to your question if you're thinking energy.
Okay.
No vector potential there at all. Now that's numerically correct, but only numerically. As we've pointed out many times now, Hamiltonian has to be an explicit function of momentum, so we got to put it back. We got to take this v dot v here and put it back. And the velocity, as you remember,
yeah, but this one,
must replace the v using p minus
all right.
a. Okay.
Okay. Yeah, that one makes sense
In order to
because
get a function of p.
yeah, that expression, yeah, is physically meaningful because vector potential is a vector, but Hamiltonian is a scalar, so you cannot have any vector in the expression for
Not by themselves.
Yeah, not by themselves.
And now we're going to have them dotted, right? And some cross terms, okay? So this is the formally correct and also numerically correct Hamiltonian. It is a function of this weird momentum, okay? The one that's been blessed by the Pope, right? Canonically, okay? That is the one that's going to make quantum mechanics undoable. Okay? So here's the thing that we would have had without an A. If I don't have an A, I'm still doing the same stuff I was doing before. P squared over 2 times the inertia, and E phi with a plus sign, not a minus sign, like the Lagrangian. Okay?
One more, Dr. Harter, like in classical electrodynamics, we can write P dot A plus A dot P as 2 times P dot A, right?
You bet, and cancel this.
Yeah.
And I'm keeping it in that form because the quantum mechanical one, these will not be equal.
Yeah. In quantum mechanics, P dot A minus A dot P would be IH bar times divergence of.
Right. There's a commutation relation. That's right. Absolutely. Yeah, so you have to be careful on it. Keep that way. Just for the purposes of being quantum mechanically correct, but we don't need that in this particular case.
I have one more question, Dr. Harter.
Yeah.
So if you are dealing with a quantum mechanical system, these would be operators. So here you would then replace this as
Perturbation.
but no, you will write P dot A plus A dot P as either 2 times P dot A plus IH bar divergence of A or whatever. Is that the reason why in quantum mechanics we always specify a gauge? When the moment we write a Hamiltonian, we specify a gauge and then say set divergence of A to be 0 or whatever.
What you can often do, and this is something I find really important, if you go to what's called a transverse gauge, then you respect the polarization of the electromagnetic wave as being absolutely perpendicular. I make A dot P equal to 0. Okay? In that particular way of looking at the light, you see the separate parts of the wave. First of all, there's the part that determines the kinks in the omegas, the kx minus omega t part, okay, and that involves a k vector, okay, the p vector equal h bar k vector, okay, pointing perpendicular to all the things that are going on as far as polarization are concerned, okay?
Right.
Now, first quantization is quantizing the values of k that you're going to have because you're in some kind of box, a cavity.
Which means the wave can have only specific momentum.
Can have specific values of p.
Okay.
Right. So that's first quantization. The second quantization is figuring out how these things, the amplitude, A for amplitude, you see, is quantized by the fact that it's in a phase space box. It's a phasor, right? X and P, making up a phasor. Now, how you want to treat that phasor, either the real part's the electric field and then there's the derivative of the electric field, or the real part's the A, and the derivative of A is the E. So you do EA as well as for a phasor, okay? But that's a, shall we say, a U2 system, okay? So is this. So there's two, U2 cross U2. This is where the relativity really gets interesting, as far as, you know, gauge and phase and all that kind of stuff. So that's the break that you do in quantum. We haven't explored that completely. This is stuff we've got to do, Al. Okay, because we've got this cavity and we've got a group theoretical way of looking at it. Let's just define all the different states of electromagnetism using group operators, and then you can do quantum field theory with group theory of translations and boosts. So this is all stuff to come later on. But for our classical purposes, this is just fine. We can redefine A and phi by gauge transformations, but it isn't going to change any of the dynamics that's going to be coming out of it, such as Hamilton's velocity equation. Okay, R dot partial derivative of A to respect to P. That's the first Hamilton's equation, right? And it works fine. There's V equal P minus A, which was our original definition. Nothing inconsistent here. It just copies our particle velocity relation. All right, so that's checking. Okay, it's a little more difficult. dp dt. Okay, this is dr dt. This one's got a little bit of meat to it. I have to take a partial derivative with respect to x, each component, x, y, and z, of both of these, because they are, in general, this one particularly, a function of x as independent variables, so it's not going to be affected by that. But I also have the scalar riding along here, and so I need a gradient, as I always would, no matter whether I had A in the mix or not. So let's go ahead and look at that. The P A dot, which is our mechanical momentum, plus the dotting of the A, is going to have this thing here twice. So I lose the 2, but each time I'm going to pick up a partial of A with respect to x in the mix here. I had a minus here before, I lose it because of that minus. And of course that one doesn't change. Okay? Now, this thing right here is velocity again. Okay? You can bring these guys in here. Okay, now this is our definition of E. So I can use that to write negative gradient of phi as partial A with respect to t plus E. Okay? That's just this equation. That's Maxwell's definition, potential definition. Only Maxwell didn't do much with potentials, but still, use that as a name. And then I'm going to turn this guy and this guy into A dot minus VA. That's the thing that we had been talking about at the very beginning of this thing. So we're coming up here with an equation for P dot where these guys cancel. The total time derivative cancels out of this, and I'm just left with the dv dt, that is the change in the Cartesian momentum of a classical particle, is equal to this. And this is a curl with a velocity scalar product. This is v curl of A plus E. Okay, that's V cross B plus E. So it checks. Welcome back. You've gone full circle. This is our vector relationship from the particle mechanics that we did to come in this way. So it all checks. Hamilton's equations Lagrange equations, all check. What does it mean? Well, it means this A is something you really have to get thinking about what it is that it's doing. It's boosting things. And my feeling is that gauge transformation can be written as a boost and vice versa, but we have to prove that. This is for non-abelian gauges as well. So I think this can be improved greatly. In the meantime, though, we're going to do some really simple stuff. We're just going to study a charge classically in a crossed E and B field. That is, we're going to have, well, let's show the colored version here. We're going to have an E field, which will be colored brown. We'll take a uniform one to start with. And no time dependence, just constant. Particle's going to run into that. The scalar potential and the gradient of scalar potential given. So the potential lines for constant field, remember our complex variable, two-dimensional, look at that. There it is. You have a Cartesian coordinate system made out of the streamlines and the equipotentials. Okay? That was for F equal a constant in the complex variable section we did before. Now, constant B field has a vector potential field that resembles a rigid rotor. That is, this is very much like a whirlpool that is a real whirlpool, one that would make a parabolic bottom to the analytic function that comes in with 1 over x squared. So analogous to this, where you go from coming in like that, surface of water coming in, and then at the bottom having a little dip. That is, and I'm going to step off screen here, and I meant to grab this little demonstrator here for rotating a field. This is just 2 Pepsi bottles glued together with a little separator here that makes about a ½ inch orifice for the liquid to flow in, and I can get this thing rotating by just turning it, and it makes a 1 over r squared if you measure radius outward from the center of that tornado. Okay. Now, if I kill that and just leave the thing rotating, well, it's sometimes hard to kill a tornado. That usually does it. But in any case, if I have rotating fluid without a drain, the fluid will, if it's got a constant curl, maintain that conservation of angular momentum, which causes it to have a 1 over r squared shape to it. And then it will finish that shape in the region where it's almost rigid rotor like this. And in that case, when you take a liquid and get all of the stuff turning rigidly, it forms a parabolic shape, which I also have over here. Let me go get this. I should have remembered to take these into range of the camera. And you're welcome to just play with this. This is epoxy, which I put on a record turntable at 45 RPMs. And I hoped I was going to make a lens, a telephoto, or a telescope sort of mirror. And it didn't work out because the epoxy wrinkles a little bit. It's certainly not optically pure. But there's a parabola. That would be the other side. And there's a brake, just like there's a brake for the force of the, the outside force, and then the inside part of this is a parabola shape. This is in this case, it's actually the shape of the surface of a liquid. And it's really remarkable. It has a brake hydrodynamic discontinuity, where it goes into a rigid object which has constant curl. So you go from outside of this, some boundary here, outside of this curl equals 0, inside curl equal a constant. So that's what we're talking about. If we have a constant B field, is a rigidly rotating vector potential velocity field. Okay, so just check that the curl of A comes out to be B. Yes, this is algebraically verified, but it's interesting geometry. Well, we're going to see that in our mechanical analog of the cyclotron effect, that is the chondromotive dynamics of, well, first of all, no electric field at all, just a rotating turntable with a ball on it will obey an equation such as we're working with here. So I'm going to take this and do some shorthand labeling here. Because if I divide through by m, I get E over m, very famous ratio, the Thomson ratio, I guess it's called. V cross B with that coefficient. And I'm going to call this one epsilon vector. And this one right here is just one component, the Z component of the magnetic field is only one active in any of these. This is 2D stuff here. So X in the electric field has a vector, but the B is just a single number. Very much like what we were doing when we were making an analog of complex variable fields and potentials. So there's my shorthand labeling, and now let's use that to write an equation for velocity. Forget Lagrangians and all that. We're just doing straight sort of sophomore physics vector analysis here. So V dot, the time derivative of V, which has two components, X and Y, is going to be the epsilon vector, the E field, with the shorthand labeling where E equal M, basic E over M is 1. Okay, and then we've got here the V, which is a two-dimensional thing, and then cross, just one component, the Z component, is all we're interested in for the magnetic part. So you end up here with a usual scalar product of the E with the unit vectors X and Y. And then you have a cross product, but just a component that is perpendicular to X and Y in the normal vector analysis. Okay? So we're using that sort of arithmetic, and why not, just for the heck of it, turn this into a complex variable equation involving a complex velocity, a complex electric field, and then just one number, this B coefficient, E over M times the Z component of B, which is the only component we have. And so we end up with an equation really very simple. It's complex velocity dot equals electric field complex function, that's EX plus I EY, and then minus I BV. The I comes from the curl, we say. That combination comes out directly from this here. Okay? I times I is minus 1. So changes that sign of this that we had before. Okay? So basically what you're doing here is replacing the unit vector EX, just like we said in the complex variable section, with just 1. I don't even write it. But EY, we replace that with an I. So that makes the two dimensions that we need to do the vector analysis with less difficulty. We can just use ordinary calculus and algebra on it. Okay? So what we're seeing here is this velocity equals this this constant term minus IBV. And what we can do is cancel this out by picking a new velocity that's boosted with respect to this velocity. So this velocity has an extra beta beta, sort of like a relativistic beta that's been added to it to literally cancel. So we end up with a much simpler equation that has just those expressions in it, namely big V dot that's got the boost inside it, okay, is equal to this epsilon minus BV, that's epsilon minus BV, and here's the V minus beta. So I just make sure that I pick the boost to be equal to the epsilon times I over B. That will get us a very simple relation for the big V, namely V dot equals a constant, complex, imaginary constant, times V. Okay? And I think you know what that is. That's V equal e to the IB, or minus IB, times the initial V. In other words, it's going to rotate it. So let's move all this stuff up here to redo it. Here's where we made the replacements, and here's our new equation in complex notation. Okay? And here's the basic idea. So what this is telling us is, and I'm going to switch over to this screen right here with the, let me sit down here so I can run this thing with a simulation for the equation that we just put up there. And let's see if it's running. Okay, so this is the particle sitting there, and if I give that particle a velocity, it proceeds to rotate. If I want to try to rotate it the other way, it won't do it. No matter where I go with this equation, I can even do down here, it's still just going to rotate left-handed. Okay, so that's this thing here with a negative B, making it left-handed. If I use a positive V, it goes this way, assuming the charge is positive throughout this. Okay, so this is a very strange motion in which every trajectory is a phasor, its own phasor. It's an oscillator that can't make anything but circles. That's an incredible symmetry. Okay. Give me a little tiny circle like that, or a great big one. They're all going to be left-handed. Now I've changed B around, I can make them right-handed. But this is what we're dealing with. And what we'd like to see is what's the effect of turning on the electric field, okay? And on this guy right here, the Vt plus beta is this V right here, and this V right here is the initial V0 plus beta. So we'll go ahead and look at that. There's the solution right there for all the general case of having both an electric field in some direction. It can be any direction, obviously. We're going to let that vary. But this is the complex form for the solution to the question of where's the velocity. Well, it's a rotation of this. That's what the velocity is. The velocity is making itself a circle, but it also has an extra term on it, so it makes an off-center circle in a sense. Okay, now we're going to see that it's more complicated than that because we have to unboost this one. So there's the complex form, easily converted back to the Cartesian form. Remember, this is a rotation. Well, it's got a minus sign on it, so it's a clockwise rotation, a negative rotation like going on there in the screen. And that matrix has not a minus sign here, has a plus sign here, and a minus sign down here to take care of that minus sign. Okay? And then here's the V. It's Vx and Vy. Okay, is a complex function before, but it has an extra I times epsilon. Okay, now epsilon is a vector, epsilon x plus I epsilon y. So the imaginary part of this thing is the y component. It's going to be down here, and then the I is going to hit that and make a real part, which is up here with a minus sign, because I times I is minus 1. Right? Then this one is the same thing. I'm doing I this. I end up with the x component down here with a minus sign, and the y component up here, minus I times plus I is a plus 1. Minus I times minus I then is a minus. So there's a vector form, the complex form of the velocity. Okay. Next step is to integrate the velocity. Okay. I have to do just a plain old integral of this function that I have right here. Okay. Well, I'm going to end up with an extra constant on this, and I can solve for that constant very easily. That's just setting the initial conditions, basically. So here is going to be my new coordinate, complex form now for the coordinate. That's the velocity. Here's the coordinate, and that's the thing that results. And that's what we want to look at in some detail. So I'm going to move all of this stuff up to the top of the screen now to make some room for turning the complex form into a vector form. Okay? So there's that same complex form for the velocity, and then there's the vector form for it. Now we're going for the integral of that velocity. Here's the complex form right there, and the numerical vector form, everything real in this expression. And by the way, only the vector form shows up in the textbook. I mentioned the complex form very briefly there, but I did it the old-fashioned way in the textbook. But this, using complex variables and eventually quaternions is a powerful way to do some stuff that we need to do. Now, let's take a picture of what this would be for an example that just gives a cycloid. I'm going to start off with that is origin. I'm going to start off at an origin or any point, but I'm going to have a velocity be 0. Okay? So with a 0 velocity, I can throw away every one of these blue terms. Okay? Those guys are out of here. Okay? And also the initial position could be 0, so I'm making that the origin. Wherever I start, let that be the origin. So this is the vector form, and there's the, this time it's ex over b squared. Now what this is showing us is that this is a rotation. This is a rotation here. A rotation of this thing. This thing is like a railroad car wheel. It's going to be turning, but it's going to be rolling without slipping on some line that's determined by these values here. So we're taking the E field here along the x-axis. Now everything's all sort of tipped over here. X is up, Z is kind of out toward me here, and Y is more obliquely into the screen here. So there's a right-handed coordinate system. Here's the electric field along just the x-axis, and I'm going to show a simulation of that in just a second here. But it's going to be, as you can see, a railroad car rotating, and if you do it right, you put the particle right on the wheel as contacting the rail. So it's this radius of the wheel of the actual railroad car that determines how rapidly the thing rotates. If this R gets pretty small and I translate, it's going to really be turning. If I make it large, then it's more like a translation. In any case, this equation here boils down to this. And you can see it's got a drift velocity plus a constant vector. Okay? And then something that's rotating. Well, that's a cycloid if we do it right. So I'm going to set this one up to do that by putting an electric field, it's like gravity. I'm going to imagine that I turn on gravity in this simulation here. So to do that, I'm going to put in a fairly healthy Y negative value. The let's see if I got this. I'm going to also make that 0, but I'm going to turn on this right here with a minus. I'll pick 2 here just to start with. I think that would make a reasonable. Let's see what happens anyway. There we go. Okay, just pirouettes off the screen. Okay. Let's put in a little bit less of a value there. I'm going to try something like, let's just see what 1 does. And basically we're setting here the force of the electric part of this. We're going to have less of a force from the electric field, this time half as much. And you can see a perfect cycloid. Okay? Now let's just play with this one. If, for example, start it up again here. If for example, I throw the thing down with a little bit of initial velocity, it's just pretty much the same. If I throw it down with a lot of initial velocity, now it's going to make a correlate cycloid. And notice how it repeats. It'll always come back to this point. It's very close to pi over 2, 1.5 distance. Okay? So let her start again. Take a really big initial velocity downward, the way gravity would want it to go. Now the correlates are just as big as the whole object. Well, let's try going the other way. It turns off too quickly for me. Let's do one more of those, and then real quickly do one of those, and then we'll go with this, go up initial velocity. You see, it's going also go through the point where I started. I can't avoid that. Okay? Now, here's an interesting one. What if I go this way? That's kind of neat, right? Do a little less velocity that way. Now I'm getting what we call prolate cycloids. I do just a little bit this way, then do a little bit more this way, and still more this way. Now I make an upside down prolate. Actually, it's not upside down. I just make one that's curling in the middle. Every one of these things always goes through the point that's pi away. So the wheel, you see, is maintaining the periodicity in space and time, which is, I think, quite neat. Okay, I'm going to have a little bit of problems for you to look at this stuff, these examples of it right here that we were just doing. But now I'd like to, just in the last, we've got about 20 minutes here, just in that time, I would like to, first of all, analyze and then show a mechanical analog for this system of the constant electric and magnetic fields that are crossed. I guess the thing that I think I find most amusing about these systems is the connection between a mechanical system and electromagnetic. Any sort of information that you can get that's an analogy is a helpful one. So let me clear out of here and then go back to the lecture and put that in things. So I'd like to show some things together with this. So I'm going to zoom through this thing to get to the, this is all of our tensor analysis here, Hamiltonian Lagrangian analysis, get a quick review here, and this system right here is what we're talking about. So what I'm saying is that a ball rotating on a rigidly rotating surface is analogous to, over here, a vector potential that is a constant rotor. Okay, that's what produces a constant magnetic field. That is, having constant curl, a table of constant curl with a non-slipping ball on it will duplicate the bizarre behavior we've seen. First of all, it will get a cyclotron orbit that goes in the direction of the whatever the omega of the table is. And that's remarkable because you would think that something on a table that's spinning, pretty fast, we're going to run about 45 to 60 or so rounds per minute RPM. You would think that such a thing would just fly off, and it doesn't do that. It does what we're pretty close to what we're going to be calculating here. So equations of motion for this thing. Now this is just a vector analysis approach to this problem. This is a problem which is difficult to do by Lagrangian methods. We'll be talking about the Lagrange constraint, Lagrange multiplier, and constraint analysis at the end of this unit 3. But for now, we're just doing it in a very pedestrian way by writing the equations of motion. Translation is equal to whatever frictional force is holding this ball to the table and keeping it from slipping. That's the requirement for this to work. But it will be obeying a equation F equal ma, F equal v dot, r dot being v. So it's r dot dot, F equal ma, right there. And the location of the position of this object, r of t, is right here, and then the velocity vector is somewhere. And the rotation, angular velocity vector, is also somewhere. Now it's free to move around in 3 dimensions, so that makes this a difficult problem in some ways, but we can find ways to make it a lot easier. In any case, we need the torque equation, the Newton's circular equation, and that's F cross R equal rotational inertia, solid ball, 2/5 mr squared is the inertia for it. And then omega dot, wherever omega is, okay, I'm going to be having a torque, F cross R, okay, F cross now this is the thing, the torque will always have to be in the plane, because the force is always in the plane. So F cross R right here will be I omega dot, and that would make you have a vector that stays up. But the thing is, you can do a gauge transformation this thing and tip that omega anywhere you want, but spinning the ball, it will not affect its motion. So that's another analogy that I find quite beautiful. In any case, here are the two equations, torque and F equal ma, equations of motion. I omega dot equal F cross R, that's the torque on that ball. That's F equal mv dot cross R, and then this is the R right here, which is always pointing in the z direction, in the same direction as omega.
But isn't usually textbooks define torque as R cross F? So I was just wondering, it's a cross.
Well,
because it's r times.
Yeah, that's true. Let's see. I think that it might be that we do have a sign thing. I usually go r cross v equal p, and then r cross p is the torque.
Is angular momentum. R cross p is angular momentum.
Yeah.
So dl by dt is torque.
Yeah, that's certainly equivalent to the thing, except for internal signs. But if you consistently do it, F cross R here. Here's F, and I would be using a left-handed rule. I could go F cross R to be the torque. So I would use my left hand. I guess I got into doing this because when you do molecular physics, you always work in the body frame, because that's where all the motion is. So everything goes with a left hand there. So this is a left-handed convention. That's what you're looking at here. Yeah. Yeah, thanks for noticing that. I think maybe I might turn it back to right. Okay. Now, no slipping. Velocity vector of the ball contact point, that's the velocity, minus omega cross r. Okay, and once again, a left-hand convention is expressing where that point is moving. I want that contact point of the ball to match the contact point of the table, that is omega cross r. Okay, this thing right here. So that is our constraint, and we're going to feed it into the equations here. So here's the non-slipping condition. This guy here equal this guy, okay, where the omega right here is a c bar, and the r is equal to the radius of the ball times that unit vector. Okay, so you end up with an omega cross the position is equal to big omega cross position. That's constant. Okay, but the variable omega right here cross this thing right here, that little unit distance times whatever that radius is the part that we need to take into account. Now the dot of this is just, since this is constant, equal to the same thing with the dot, making a velocity right there of the position. Now let's see if this is, yeah. And then the constraint is demanding that velocity be this right here, which is omega cross v plus omega dot cross c. So we can put these two together. Okay, we got here v dot equal omega cross r dot, and then plus omega dot cross z. And I'm going to write this as it was written up here. Okay, and finally get here that the acceleration of v is equal to omega cross v plus this omega dot crossed with the z-axis. Now I'm going to take this triple cross product apart with that identity. So here we have b being the, let's see if that's right here. Yeah, b being the v dot, c and a are both the z-axis with a radius on it, so we get an r squared out of that. Here we get an r squared with the v dot, but here we get this combination here, v dot z, which can be set to 0 because v cannot have any component unless the ball hops off up and down on the table with r. So there's the equation right there. It's 1 plus mr squared over I. Now that's 1 plus mr squared over 2/5 mr squared. So this is 1 over 2/5. That's 5 halves. 5 halves plus 2 halves is 7 halves. Remember that number, 7 to 2. That's the thing that determines the charge that this ball has. It's depending on, you know, how dense is its center or whether it's a hollow ball. Is equal to omega cross velocity. So the omega is like a magnetic field, B cross V. And then this is the charge. And then there's the V dot that we get for this thing. So this thing should behave like a charged particle in a magnetic field. Now if you want an electric field, you just tip it. And this device over here is designed to do a little bit of electric field in addition to that. So let's go ahead and see if we can get it to work.
So what is that, Dr. Harter? That big box on the bottom?
Well, the big box is simply a little carriage that lets you might as well move over here so you can actually throw balls at this thing and watch it, hopefully, behave. It's sort of a delicate operation here, but I'm going to turn up the magnetic field, get that vector potential rotating, and I think it'll work pretty well right around 30 miles per hour here. So I've got a scale here, 0 to 100 actually. But let's just keep it slow for the beginning. Anyway, I'm going to just, the way you get it started without having it jerk out of your hand is put it close to the center and then give it a kick. That was a pretty good one. And it goes back pretty close to where it came and then slips a little bit, so it isn't perfect. But you can see it, if I just give it a little kick there, this thing will go 2/7 as fast as the table. So if I count what the table is doing, 1, 2, 3, 4, 5, 6, 7. I should have gotten 2 full rotations of that ball during that time. Try it again.
When you say 2 full rotations, you mean to say like it
Yeah. How many times does this thing make it circle your orbit? You see. Okay? 1, 2, 3, 4, 5, 6, 7.
Yeah.
Just coming by. Pretty close. Okay? Now as you increase the magnetic field, it just makes tidal circles like our simulation on the computer did. We'll go up here and go roughly twice as fast. Now the trouble is now that if it gets toward the edge, the centrifugal force is finally too much for the stiction, and it'll break from the thing. But still, give it a good kick here. There was 2. That was 7 thing. Now if I turn on the electric field, okay, say I put the electric field sort of that way, you can see it's getting out to the edge. Now I'm going to try to reverse that before it breaks. Bring the electric field back toward me, and it goes toward you perpendicular to the electric field. Of course, cycling. Now you can hear it slipping. Okay, it's gotten a bigger orbit, but still it's working its way towards you at a small drift velocity. That's determined by this, whether I can save it or not. Now what I can do is I can resonate this thing when it gets out of control. If I know what I'm doing, I stick it in the pi/2 slot. Now we'll talk about resonance in Unit 4. But basically what I have to do is simply, first of all, if I follow the thing around just without paying attention to it, I get the thing to cyclotron up to a, larger amplitude. Now I'm going to try to make it come to a smaller amplitude. And the way I'm going to do that is just follow it around. That's increasing it. Now I'll get behind it. I'm not kidding. I've got to catch up with it, keep up with it. At pi/2, I have to do this at pi/2. Pretty close. I got it to 0. Okay, so it's behaving like a cyclotron with a cross-electric field that's varying. Okay, and I've got it turned up more or less off right now. And it's doing its usual 2 to the 7, 2 to 7 ratio. Now if I slow it down, adiabatically, usually I could hold it on the table, but right now it's not working. I speed it back up again. Oh, I did it the wrong way. That's called parametric amplification, which we'll talk about also. Okay, it's actually changing the parameters of the spring constant, if you will, of the oscillator. Anyway, come on and fool around with the thing. It's kind of fun, and you should realize that it's not a function of size of the ball. Those are both going at the same frequency. Go ahead and stick another one on there.
So this is to control the electric field, is it?
That's just controlling the B field, yeah, the analog B field. And I'm going to slow it down because the steel one is slipping. Picked up some dirt. You heard it bouncing. There. That's what cyclotrons do. They throw the particle out the edge. Go ahead and stick it there. They can run into each other. Except that they won't, because they're orbiting at the same speed. And the steel didn't catch it either.
So you basically use the electric and magnetic field just to rotate the disc, right, at the bottom?
Well, there's just a motor in there that's turning
the disc. So
the disc.
The whole idea is to
get the disc at a constant angular velocity. Yeah, which would be constant B. Go ahead and put one right next to it in the center there. Let them touch each other. They're sort of following each other around a trajectory now. But one of them's a little dirtier than the other one, so it bounced a little bit and slipped.
So, Dr. the calculation that we did, that you showed us just now, the 2/7, is the ratio of the revolutions of the disk to the smaller ball.
Right.
I mean, the smaller ball to the
yeah,
disk.
1 plus 1 over inertia coefficient.
So we don't take into account the rotation of the small ball about its own axis, right?
Well, here's the interesting thing. I can put this ball in here. Now see the numbers in there? Okay? I put this thing on there, in the center, and spin it like mad. It doesn't make any difference. So now I've added an extra omega component,
Yeah.
you see, in this direction. What it would like to do is just keep the omegas always this way so that they can serve as its accelerate. You can visualize that more easily. But
we don't take this
you
omega into
can
account.
see where the omega is. You see where the omega is?
It's rotating.
It's sort of at
this direction.
yeah. It's not quite perpendicular or parallel to the table. Normally, what I would do was make sure that the omega, now the omega is more close to being perpendicular to the table. But we have this extra gauge term that isn't going to affect the motion of this thing at all.
So because we haven't taken this omega into account in that calculation. So.
We aren't taking it into account because it has no effect.
Yeah.
Yeah. Now, it really does have a little bit of effect because the more you turn it, you get extra friction and you hop over more things when the ball has got that extra component.
If we increase the speed of the rotation of the bigger disk, then the omega should also increase, right? Because it's going to spin faster.
Yes, yes. If it doesn't fly off, if it doesn't break free. It's still 2 to 7 except for the skidding. It's gonna break. There you go. Yeah. So anyway, if you can figure out a game that people would pay
And what
for.
happens if you apply a force with your finger to it?
Oh, it goes crazy because it's always acting perpendicular.
It will. act at a right
good.
angle to the
Yeah.
force you're
I
applying.
mean, it's annoying. That's why I don't put it out here. You know, it's really hard. You know, if you want to go bung like that, you can sometimes make it behave. You see, but you have to do it real quickly because it wants to just turn around your hand. Anyway, Maxwell thought very hard about the electromagnetic field using mechanical analogs. None of them really panned out. I think he would have been happy to see this one, but this is a very simple part of the electromagnetic story. But anything you can get that puts a handle on understanding electromagnetism, we still need it.
So in which chapter have you discussed this one in the textbook, Dr. Harter?
Oh yes.
Which unit 2?
Yeah, it's in yes, it is in Unit 2, I think. That's right. Yeah.
Unit 2.
Okay, I think that's a wrap. I'm glad it worked because this thing has a tendency to go crazy, and I have to go down to the shop and put in a new set screw and all that kind of stuff.